Hi guys, this is John Heshmat and welcome to Physics Simply. In this video, I'll be covering the basics of DC circuits or direct current circuits for IGCSE and AS level physics. You can see here we have two electrical cells, an ammeter, a voltmeter, two light bulbs and two switches. We also have some connecting wires. First, we start with the concept of a simple circuit. For any circuit to work, you must have a source of EMF or an electromotive force. Here we have the cell of EMF 1.5 volts as a source of voltage or potential difference. This potential difference is caused by the positive and negative charges on the terminals of the battery. Now we are going to connect something simple as a light bulb to the battery or to the cell using these connecting wires, and we're going to be using a switch to switch on and off the light bulb. Now you can see that the circuit is connected. We have the source of EMF, which is an electrical cell of EMF 1.5 volts. We have a wire connected from the positive terminal to one of the bulb's terminal. From the bulb, we have a wire connecting to the switch. From the switch, we have another wire that connects it back to the negative terminal of the cell. But even though there is a source of energy or an EMF, the light bulb is still not working. That's because there is an air gap in this section. We call this an open circuit. The charges are ready to move. The free electrons in the wires and in the light bulb are repelled from the negative terminal of the battery and are attracted towards the positive terminal of the battery, but there is no closed track for them to move because air here is a poor conductor. So once I close the circuit, the light bulb starts to glow. It's glowing dimly, which means there is a low current in the circuit here. Now, how the energy is transmitted through the circuit, that's when a charge is passing into the battery. It has a low energy or low electrical potential energy. As it goes into the cell, it gains some electrical potential energy and uses this energy to flow through the circuit and give some light and heat through the light bulb and goes back to take some energy and so on. Most of the energy here is given to the light bulb and some is dissipated as heat into the wires. Now you can see that I've connected two cells into the circuit here. Now we can call this a battery. One cell is just one cell. When it's more than one cell connected, it's called a battery. You can also notice that I've put an ammeter here connected to the circuit or connected to the light bulb and the switch. When there is only one path for the charges to move, this is called a series connection. When we connect an ammeter, it's always in series, connected in series, which means you have to disconnect the circuit and put the component and then reconnect. This is called a series connection. Now, when we close the circuit, you can see that the light bulb works and the ammeter shows a reading of 0.22 amperes. That means that through this section of the circuit, there are 0.22 coulombs of charge are moving. Remember, 1 coulomb contains 6.25 times 10 to the power of 18 electrons. That's 6.25 million electrons. You can notice here that the light bulb is shining brightly. That's because of the higher EMF. When I connected two cells in series here, the voltage increased or the EMF increased, which increased the current. Now we need to understand how energy flows. For this, we are going to use a voltmeter. Remember, an ammeter and a voltmeter always have terminals, a positive terminal and the negative terminal. The positive terminal must be pointed towards the positive terminal of the battery, and the positive terminal of an ammeter must also be pointed towards the positive terminal of the battery. So with the negative, it should be towards the negative terminal of the battery. Now, we're going to measure the potential difference or the EMF of the battery. Now the voltmeter shows a reading of 2 volts. This means that every coulomb of charge entering this battery will gain 2 joules of energy as it goes through the battery. Now remember that we had to disconnect the circuit in order to connect the ammeter, but for a voltmeter we just connected it across the component we want to measure the voltage across, which means that this is not a series connection. When there is a branch of wires here, like this one, we call this a parallel connection. So a voltmeter is always connected in parallel. Now, if you want to measure the voltage across the bulb, we just disconnect the voltmeter and connect it across the bulb. Now the voltmeter here is showing a reading of 1.6 volts, which means 1.6 joules from each coulomb of charge is given to the light bulb, and the rest is distributed as heat through the other components, including the connecting wires. So if we need to know the voltage across one wire, for example this one, we just connected the negative terminal to the negative terminal of the battery and the positive terminal to the other end of the wire. Now the voltmeter is almost reading 0, which means this wire almost takes no energy from the charge as it passes through the wire. Now we mentioned that a voltmeter must also always be connected in parallel and an ammeter must always be connected in series. But what happens when we connect cells in parallel and in series? You see here there is only one line for the chargers to pass through, which means that these two cells are connected in series. To know how the voltage changes or the potential difference changes across a battery connected in series, we must first measure the voltage across one cell. Here the reading is almost 1.3, and the other cell is also 1.3. But when we measure the total potential difference or the total EMF given off from the whole battery, we get a reading of 2.6, which is the sum of the two EMFs. This means that when we connect cells in series, the potential difference increases, or the EMF increases, and it is equal to the sum of the potential differences of the cells. Now I've connected the two cells in parallel. You see here the two positive terminals are connected together and giving us one positive terminal, and the two negative terminals are connected together, giving us one negative terminal. Now we're going to see how the potential difference changes when a parallel battery is connected. Now the voltmeter is reading 1.3 volts, which is the same voltage of one of the cells. This means that connecting cells in parallel does not increase the voltage, it keeps it the same. What's happening here is that if 1 coulomb of charge is passing through this wire and entering the battery, it can either go through the upper cell, gaining only 1.3 volts, or through the lower cell, gaining only 1.3 volts. When we connected it in series, the charge had to go through two cells. So first going through the first one, gaining 1.3, then going through the second one, getting another 1.3, giving us a total of 2.6 volts. But here it's not the case. Here a charge can either go through the upper cell and passing on, or through the lower cell and passing on. Now I've connected 3 cells in series, giving us a voltage of 4 volts, or an EMF of 4 volts. That's with the right orientation. So you see here positive, negative, positive, negative, positive, negative. But what happens if we change the polarity of one of the cells? Now I've connected the middle battery or the middle cell in opposite orientation or in opposite polarity. You see here negative, positive, positive, negative, negative, positive. This causes the chargers to lose energy as they go through this cell. And as you can see, the voltage here is now only 1 volt. This means that there is no addition of the EMF, but we had to subtract some. What happens here is a charge goes through this cell, gains some energy, And since the polarity is the same here, there is some resistance or some opposition from a force or repulsion force. This causes the charge to lose energy as it goes through this cell. And then the final cell gives it some extra energy. That's what is recorded in the voltmeter. Now we can also connect two light bulbs in series. In this circuit, you can see that there is only one path for the charge to move through the battery to one light bulb, through the ammeter, and through the other bulb, and then back to the battery. Since there are no branches or no sections through which the charge can be divided, this is called a series connection. You can see that the ammeter is showing a reading of 0.12 amperes, and the two light bulbs are lit. They are working. Now, when there is a series connection, if any connection is opened, the current stops and both light bulbs immediately stop working. Once the connection is remade, the current keeps moving again. If one of the light bulbs gets damaged, there is an open circuit and the whole circuit stops working. There is no current and the other light bulb goes out, which means that all the components in the series connection depend on each other, and there cannot be any defect in any part of the circuit. Now, how does the voltage change across a series connection? Now, if we measure the voltage across the first light bulb, here we have a reading of 1 volt, which means that every coulomb of charge passing through this light bulb will lose 1 joule of electrical energy and converts it into light and heat through this bulb. Now we are moving to the second bulb. This light bulb is taking 0.9 volts of energy. This means that every 1 coulomb of charge passing through this lamp will lose 0.9 joules of energy. Now we can go and measure the total potential difference across the battery. Now the reading across the battery says 2.2 volts. This means that each coulomb of charge passing through the battery gains 2.2 joules of energy. 1 joule of that energy is given to this light bulb and 0.9 joules are given to that bulb. So that makes 1.9 volts. So 1.9 volts are given to the lamp. And the rest, which is 0.3 volts, are given to the wires and the ammeter as heat. But they do not work or considered a useful energy. Now notice that the total of the voltages across the component is equal to the potential difference given through the battery. So potential difference is divided across a series connection. The battery gives some voltage, some of that voltage is given through to the wires and the ammeter, and the rest is divided across the lamps. Also, take care here that this one took 1 volt and this one took 0.9 volts, which means that they are not identical. So the voltage isn't always divided equally if the components are not identical. Now let's redirect our attention to the current in a series connection. You can see here that the current between the two light bulbs is reading 0.12 amperes, but how does it compare with the rest of the circuit? For example, let's measure the current across this wire or this section of the circuit. You can see that the voltmeter still reads 0.12 ampere. This means that the current through this section is equal to the current through that section, and it will also be equal to the current in this section. So in a series connection, the voltage of the battery is divided across the components. So the voltage across this lamp plus the voltage across this lamp and the voltage across the wire is equal to the total potential difference or the EMF given by the battery. But when there is a current, the current is the same through the battery, the components, and the wires. All is the same. Now we've changed the connection from series to parallel. You can always recognize a parallel connection through the branching of the wires. You see, this wire is entering this junction, and there are two branches, one going to this bulb, and the other branch is going to the other bulb. When there is branching, there is always a parallel connection. Same here. This wire is entering one branch to the switch and the other branch to the other switch. Now, you can notice that the brightness of the lamps is greater in a parallel connection. What happens if you disconnect one of the light bulbs? See, this one went out, but this one keeps working. This is because there is always a closed loop. You see here the charge can pass this way through this lamp and then goes back without having to pass through this section of the circuit. But what happens when we connect two lamps in parallel? You see, some charges go through this wire, part of the charge goes through one lamp, and the rest of the charge goes through the other lamp, and then they meet again at this part and move together to go to the battery. That's what happens in a parallel connection. The charge is divided, which means that the current is probably divided too. But what happens to the voltage? Let's measure some voltages. Now we're going to measure the potential difference across the battery. Here the battery is reading a total voltage of 1.5 volts. Now let's read across one of the light bulbs. It also reads 1.5 volts, and the second one and the last one. This one also reads 1.5 volts. This means that the voltages are not divided in a parallel connection. They were divided in a series connection, but in a parallel connection, the voltage of the battery is the same as the voltage going through one bulb, is the same as the voltage going through the other bulb. So all components in a parallel connection takes the full voltage of the battery. That's why the lamps are shining brighter. But what happens to the current though? Now when you connect an ammeter in series with the battery, it reads the whole current going through the whole circuit. This ammeter is reading now 0.32 amperes going through this battery and through this wire. This means that 0.32 amperes will be divided across these two branches. Let's see the reading across this branch. Now the reading across this branch is showing an 0.15 amperes or 0.16 amperes. Let's change the connection and see the other branch. Now this branch is also reading 0.16 amperes of current, so 0.16 amperes through this branch and 0.16 amperes going through this branch, they all add up to 0.32 amperes going through the whole circuit, and then they are divided and go back and so on. So now we discussed that the potential difference is the same across all components in a parallel connection. But what happens if one of the connections is severed? Now the other light bulb keeps working and the current in it is the same, which means that the circuit is still taking the total voltage of the battery and giving the same current. But what happened to the current through the battery? So now I've reconnected the ammeter to read the total voltage of the circuit. You can see the ammeter here is reading 0.32 amperes with the two light bulbs working. What happens when I disconnect one of the light bulbs? Now the ammeter is showing a lower current. This means that once one of the connections is severed, the battery will only supply the current needed to feed one of the components. So the current is not always the same. It changes through the battery. The more components you place in parallel, the higher the current the battery will supply. Now you see I've connected a large battery of 4 cells connected in series with one lamp, and there is a branch here, which means that this section of the connection is in parallel. So some charges go through this light bulb and go back to the battery, and the rest of the charge goes through the other bulb and go back to the battery. Now you can see that this lamp is shining very brightly and these are hardly lit. This means that this lamp is taking most of the voltage or the potential difference of the battery, and these two have very small potential difference. So let's measure that. So the voltage across this lamp alone is about 6.5 volts or 7 volts. The reading across this lamp is 0.5 volts. The reading across this lamp is also 0.5 volts since these two are connected in parallel. So there is an 0.5 volts across this section of the circuit, and there is about 7 volts across this section. That makes a total of 7.5 volts. Still, this part takes a different voltage than this part. This means that these sections are connected in series. So you have a lamp connected in series with two lamps in parallel. Once we sever one of the parallel connection, you can see that those two lamps are lighting almost the same. This is because there is no more parallel connection. This section is no longer in parallel, and we have only two lamps which are almost identical connected in series. So there is only one path for the charge to move here. I hope you've enjoyed this video. If you did, please like and subscribe to the channel so you can follow up on the upcoming videos about circuits and other physics topics. Thank you and goodbye.